Have you ever stopped to think about what makes your voice, well, your voice? Today, we're going to dive into the incredible science behind the sounds we make every single time we talk. We're getting right into the physics of speech itself.
I mean, think about it. You can recognize a friend's voice on the phone in, what, a second? Even before they say their name. So what is it really in the sound alone that carries so much information? It seems so simple on the surface, but the answer is this fascinating mix of biology and physics.
All right, so let's treat the unique quality of every single voice like a scientific puzzle. It's a puzzle we can actually start to piece together, just by looking at the sound waves we all produce.
Right. We all know the words we choose tell a story. That's obvious. But what's really wild is that beyond those words, the physical sound waves we create, they contain a huge amount of information. And guess what? There's a whole field of science dedicated to decoding that very story.
So what's this field called? Let's go ahead and put a name to the science that studies the actual physics of how we talk.
It's called acoustic phonetics. And what does that mean? Well, it's the study of the physical properties of the speech signal. In other words, it treats your speech not just as language, but as a measurable physical event, just like a radio wave or a beam of light.
In this quote, it just nails it. It's not just what you say, it's the sound waves you create. So for a second, forget the meaning of the words. Just focus on the sound itself, that hum, that hiss, that vibration. That's the raw data that acoustic phoneticians get to play with.
Okay, so if we're studying these physical properties, what are they exactly? What are the basic building blocks that make up a speech signal? Let's take a look at the two fundamental ingredients that our source material points to.
First up, we've got something called formant frequencies. Now this sounds technical, but it really just points to the musical resonant quality of our voice. These are those rich tones that get produced when our vocal tract acts like a little resonant chamber, and they're what give vowels like ah, e, and oo their totally distinct character. And then you have the second ingredient, friction noise. And this is, well, it's pretty much the complete opposite. It's not musical at all. It's the sound of turbulence, just air being forced through a really narrow passage. Think of that sharp hiss in the sound s, or that breathy puff in the sound f. That is friction noise. Let's actually try this out. Go on, say hello. You can feel that open, vibrating, resonant O sound, right? That's the formant frequency doing its thing. Now say hush. You can totally feel that sharp, airy sh sound that's created by pure friction. Our speech is this constant, super complex dance between these two types of sound.
Okay, so we've got our ingredients, formant frequencies and friction noise. Sounds pretty straightforward, doesn't it? Well, here's the twist. In the real world, analyzing a speech signal is anything but simple. It is a genuine puzzle.
You know, we don't speak in perfectly soundproof labs. Our voices don't exist in a vacuum. So the raw speech signal that a microphone picks up is, well, it's messy. And trying to do a straightforward analysis gets really complicated by all the noise of the real world.
Our source material points out these three huge challenges. First, you've got just plain old background noise, a car driving by, the hum of an air conditioner. All of that gets mixed into the signal. Then you have the massive differences between us as speakers. Anatomical differences mean the literal size and shape of my vocal tract is different from yours. And then physiological differences, that's stuff like how fast we talk or our breathing patterns. All of these variables completely change the physical sound wave.
But here's the crucial insight, the really cool part. These complications aren't just problems that we need to filter out. They are the very thing that scientists study. Acoustic phoneticians analyze all these variations to figure out everything from how voice recognition software can tell speakers apart to how our brains somehow manage to understand what someone's saying in a noisy restaurant. The puzzle is the point.
Which kind of leaves us with this final thought. We've seen that speech is this incredibly complex, unique physical signal, shaped by our bodies and our environment.
It really makes you wonder, doesn't it?
If every voice is so unique, what other secrets are still hidden in the sound of our speech? What else could we learn just by listening a little more closely to the physics of how we talk?